In previous chapters, we looked at the effects of pulling and pushing on objects. Chapter 7 looks at the effects of twisting a solid or hollow shaft. We will calculate the stresses that develop and the amount that a shaft twists under a given torque. If we apply a torque T to a shaft, it will twist by angle theta as shown at the bottom left. A shear strain develops in the shaft, which is maximum at the surface and zero at the very center. If the shaft is twisting elastically, then the shear stress is proportional to the shear strain, so the maximum shear stress is at the surface and it's zero at the very center. Consider a small area that we'll call lowercase a, which is located a distance r from the centroid. The shear stress acting at this location is a fraction of the shear stress at the surface. The fraction is r over c, so the closer to the surface we are, the higher the shear stress. Shear force is shear stress times area. Torque is force times distance from the centroid, so multiply the shear force times r to get the torque acting on our little area A. If we add up all the little areas that constitute the cross-section, we'll end up with a constant times the sum of r squared. In Chapter 6, we saw that the sum of a times r squared is the polar moment of inertia of a solid circle. So we can plug in the polar moment of inertia into our equation. Usually, we don't bother with the subscript max because we're only interested in the maximum shear stress, which is at the surface. We can rewrite the equation to solve for shear stress as a function of torque and the dimensions of the cross-section. Here's an example problem. A solid round shaft is loaded with a torque of 2 kilonewton meters, and we want to know the shear stress. We start by solving the shear stress equation algebraically in order to simplify the equation. It works out to 16t over pi d cubed. The result is 81 megapascals. We can compare this number with the allowable shear strength for this material and determine whether the shaft is strong enough to support the applied torque. What if the shaft is hollow? Lowercase c is still the distance from the centroid to the outer surface, whether or not there is actually shaft material at the centroid. The polar moment of inertia equation is a little different, so the stress equation will also be a little different. The most common mistake in this type of problem is calculating dO to the fourth minus dI to the fourth. If you take the fourth power of dO minus dI, you will get the wrong answer. The second part of the chapter is about calculating twist. There's a derivation you can read up in the book, but let's focus on using the results. The angle of twist, Greek letter theta, equals the shear stress times the length of the shaft divided by the shear modulus of the material and the value c. You can find numbers for the shear modulus, capital G, in Appendix B. It's important to know that the angle of twist is in radians. So if you want the answer in degrees, you'll need to convert from radians to degrees. You can make this conversion in one of two ways. The clearest way is to include it in your unit conversions by setting 180 degrees equal to pi radians. The other way is to use the radians to degrees button on your calculator. The ratio of 180 to pi is about 57, So if you forget to make the conversion, your answer will be off by a factor of 57, which in most industries is significant. If you do the conversion in the wrong direction, your answer will be off by a factor of 57 squared, which is about 3,300. In every industry, if your answer is off by a factor of 3,300, it's significant. If you substitute the shear stress formula into the angle of twist formula, you'll get a different formula for angle of twist, which is torque times length divided by polar moment of inertia and shear modulus. Now you have two equations for angle of twist. Which one is best? It depends on the problem you want to solve and which variables you already know. In this example, we are twisting a 6-foot-long, 2-inch nominal diameter Schedule 40 steel pipe with a torque of 400 foot-pounds. We can find the dimensions of the pipe in Appendix D, including the polar moment of inertia. We can find the shear modulus, G, in Appendix B. Now we use the second of our two twist formulas, and we find that the angle of twist is 1.24 degrees. Let's take the same pipe, but twist it until it reaches its allowable shear stress of 20 ksi. We use the other angle of twist formula and find that it can twist 5.8 degrees before reaching its allowable shear stress. Therefore, the torque in example number 2 is not enough to cause the pipe to permanently deform. Some shafts have more than one diameter. Where the two diameters meet, there is a radius of curvature, r. If r is too small, we can have a stress concentration. We solve these problems using a chart, then plug the K value into our stress equation, just like we did with stress concentrations in plates loaded in tension. Here's how it works. We have a stepped shaft with diameters 2 centimeters and 4 centimeters, with a 1 millimeter radius between them. We can solve this problem in 5 steps. Step 1, calculate r over little d and find the value on the horizontal axis on the chart. Step 2, calculate big D over little d and pick the right curve on the graph. Step 3, run a line up from r over little d equals 0.05 and then cut across where it hits our curve. The value of K is about 1.72. Step 4, calculate C and J using the smaller shaft diameter. Step 5, the shear stress is K times TC over J. This process is very similar to what you've already done in stress concentration problems for plates in tension back in Chapter 4.